Hello everyone, my name is Honesto Pardede. I am mechanical engineering student from Udayana University, and I'm here to represent about metallurgy, fabrication and finishing of metal products. I got the references from Metallurgy for the non-metallurgist, edition by Arthur C. Reardon. For the content, we got 6.1 deformation process, 6.2 primary production mills, 6.3 forging, 6.4 drawing and extrusion, 6.5 forming, 6.6 powder metallurgy, 6.7 material removal processes, 6.8 joining process. Before we got to the first content, I got in the explanation first. Metal product. They are subjected to mechanical production operations. Subsequent to casting and solidification are referred to as wrought products. These products can be shaped, finished, and assembled by using a variety of metalworking techniques, which may include methods for forming, metal removal, and joining. Depending on the alloy system and the intended application for the finished product, there are a staggering number of production techniques that may be employed. The possibilities range from high volume mill production, as we can see in figure 6.1, to the manufacture of complex parts by powder metallurgy in figure 6.2, and or the joining of thin foil by ultrasonic welding, as we can see in figure 6.3. Let's jump to the first content. 6.1 Deforming processes. In metalworking processes, a workpiece such as a billet or a blanket sheet, for example, can be plastically deformed by a set of tools or dies to obtain the desired final thickness and geometrical configuration. Metal forming processes can be classified into two general categories. First is a bulk or massive forming operation, and second, bending and sheet forming operation. Sheet forming is sometimes simply referred to as forming in the broadcast and most accepted sense. However, the term forming can be used to describe both bulk deformation processes. Sheet forming and bending processes. Forming is performed through contact between the surface of the deforming metal and tool. The nature of the material flow or plastic deformation primarily depends on the type of forming processes that is used, the temperature, the applied loads, and the frictional stresses between the tool and the workpiece material. In first figure, as we can see in figure 6.5, flow stresses versus amount of deformation for 304 stainless steel at A cold and warm working temperatures, and B working hot temperature. The hot and cold working metals can be mechanically worked over a range of temperature. Higher temperature can improve workability characteristic, although may wrought products are cold work in order to achieve certain mechanical properties, or sometimes they are warm work for other specific purposes. One advantage of cold working is strengthening. During cold working, the mobility of dislocation is lowered as they become tangled up to networks and pile up at grain boundaries. This leads to strain hardening, which make further deformation more difficult to achieve. In figure 6.5 in a point A, in figure A. Slightly higher warm working temperatures, the degree of strain hardening is reduced, so the flow stress is reduced at higher strains, in figure 6.5 in figure A. Although most cold working is often performed at ambient temperature, the dividing line between cold and warm working is not exact. One definition of warm working is when workpiece temperature is more than 3% of the pre-crystallization temperature, or on an absolute scale, but lower than the recrystallization temperature of the material. At temperature above the recrystallization temperature, the process is referred to as hot working or hot forging. During the hot working, the strain hardening effect is greatly reduced and the material flow stress remains nearly constant with increasing amount of deformation. Under this hot working condition, the dislocation generally generated during plastic deformation are quickly dissipated by recovery and recrystallization mechanism, in which the elongated grains reform into smaller equized grains. As we can see in figure 6.6 that I can show you here, the microstructural variation during A, cold working, and B, hot working. Equized grains in figure 6.6 in B1, as in steels and nickel alloys, or equized subgrains are formed within the elongated grains as in aluminum alloys. Next slide, we got 6.2 primary production mills. In primary production operation, the initial stage of metalworking involves the breakdown of a cast structure into a rod or work form. The starting material is usually either an ingot from static or stationary mold, casting or continuous cast slabs or billet. With conventionally cast ingot structure, workability is very low due to relatively coarse microstructure and extensive segregation of impurities. Thus, ingots undergo a primary reduction step that consists of either forging or rolling, as they are processed into semi-finished shapes. Continuously cast alloy requires the primary reduction step, as we can see in figure 6.7. The uniform unbroken grain flow amount around the contours of the fork head of a threaded fastener. The uniform unbroken grain flow minimizes stress raises and unfavorable shear planes and therefore improve fatigue strength. The next step is the mill processing of bloom, billets, and slabs to produce various product forms such as plate sheet, strip, and bar. As we can see in figure 6.8, the production mill processes. And ingot breakdown. Many ingots continue to be statically cast because not all ferrous and non-ferrous metal are capable of being continuously cast. Due to their relatively coarse and inherently weak microstructure, the temperature range over which ingot structure can be forged is very limited. Typically, ingots must be hot worked to refine the grain structure in order to allow recrystallization to occur. Hot working is usually performed at temperature greater than 3/5 of the absolute melting point of the alloy, as we can see in figure 6.9, which I make there. Schematic illustration of relative workability of cast metal and wrought and recrystallized metal are cold, warm, and hot working temperature. The melting point for solidus temperature is denoted as MP, or cast metals, or MP, the wrought and recrystallized metals. Next, we got 6.3 forging. In its basic form, forging consists of applying compressive stresses to a piece of metal, known as the workpiece, between a pair of dies in order to permanently change its physical dimension or geometry. Large forgings are processed by primarily mills, but forging also purchase wrought product in the form of bars, billets, or blooms. For subsequent forging or hammers and presses, the goal of most forging operation is to produce a part as close to the finished shape as possible. Forged products include crankshaft for car engines, adjustable wrenches, hammers, rotors for steam turbines, and landing gear components for aircraft. Drop forging and press forging are the two most general types of forging processes. In drop forging, a hammer is raised up, then dropped onto the workpiece. To deform is according to the shape of the die that is used. There are two general types of drop forging: open die drop forging and closed die drop forging. As the names imply, the former does not fully enclose the workpiece, while the latter does. Press forging work by slowly applying a continuous pressure of force which differs from the near instantaneous impact of drop hammer forging. The amount of time the dies are in contact with the workpiece is measured in seconds, as compared to the milliseconds of drop hammer forks. The press forging operation can be done either cold or hot. The main advantage of press forging as compared to drop hammer forging is its ability to deform the complete workpiece. Various types of forging processes are listed in table 6.2, which I make there. The forging processes, because forging is a relatively complex process, fracture or generation of undesirable defect can occur in the workpiece. Some types of metallurgy defect are summarized in table 6.3, which I can show you too. The common metallurgical defect in forging. Then we get to roll forging, also known as hot fork forging. Also known as hot fork rolling, is a process for simultaneously reducing the cross-sectional area and changing the shape of heated bars, billets, or plates by passing them between two driven rolls that rotate in opposite directions and have one or more matching impression in each roll. The principle involved in reducing the cross-sectional area of the work metal in roll forging are essentially similar to those employed in rolling mills to reduce billets to bar. However, a shape change across the width and or along the circumference of the roll makes the process especially attractive for certain applications. Roll forging essentially combines the advantage of rolling and incremental forging in one, as you can see in figure 6.11. Comparison of typical design limits for rib web structural forging for point A is aluminum alloys and B nickel-based alloys. Dimension given in millimeters. We can see this picture in millimeter scale. In figure 6.12, we can see a typical deformation sequence in closed die forging of rib web part, showing how lapse can be generated in preform geometry is selected improperly. Next, we get to the drawing and extrusion. Drawing and extrusion are based, respectively, on the pulling and pushing of section through dies. In the drawing process, the cross-sectional area and or shape of a rod, bar, tube, or wire is reduced by pulling it through a die. The deformation is accomplished by a combination of tensile and compressive stresses that are created by pulling force at the exit from the die and by the die configuration. As I can show you in figure 6.16, the drawing processes. Drawing is one of the oldest metal forming operations to make long products with excellent surface finish, closely controlled dimension, and constant cross-section. Wire and tubes are drawn in a similar manner. The general practice is to place a mandrel, also called a plug, or a solid bar with a blunt end inside the tube. As the tube is drawn, metal flows past the mandrel, which controls the inside diameter of the tube and supports it during deformation. And then we get the extrusion. It's a deformation process used to produce long, straight, semi-finished metal product such as a bar, solid, and hollow section. Tubes, wires, and strip. The favorable compressive state of stress during extrusion allows high capacity for deformation, and so it is possible to extrude metal that can be only slightly deformed by other methods. Practically, all metals can be extruded, although the capability of many alloys to be processed in this manner falls within a narrow range of processing conditions that depend on a variety of application-specific factors. Special techniques to extrude different materials are to a large extent dependent on the extrusion temperature and room temperature. Extrusion is economically feasible for low melting alloys and some aluminum alloys, while hot extrusion is required for harder alloy. We got hot extrusion technology. Pre-rolled billets or round ingots can be worked in an extrusion press with an open-ended die. Remove the metal through the die, which determines the shape of the extruded shape. For hot extrusion working, the billet temperature is typically greater than the required to sustain strain hardening during deformation. This is generally greater than 60% of the absolute melting temperature of the metal. The hot extrusion process is used to produce metal product of constant cross-section, such as bar, solid and hollow section tubes, wire and strip, from metals that cannot be formed by cold extrusion. Then last we got cold extrusion. In this process, metal is squeezed or squirted through a hole in a low melting point, and relatively ductile metals such as aluminum, tin and lead are easily extruded. The most commonly cold extruded metals are, in order to increasing processing difficulty, aluminum and aluminum alloy, copper alloy, low and medium carbon steel, modified carbon steel, low alloy steels and stainless steels. Special glass lubricant are used for the cold extrusion of certain steels. Next we got to 6.5 forming. Metal bar, tube, plate and sheet are formed by various bending, stretching and drawing operations. Bar and tube are formed mainly by bending operations such as compression bending, stretch bending, row bending and roll bending. Forming includes various bending, stretching and drawing operation, plus some special method to develop surface with deep resist, spinning, deep drawing or shallow resistance. Spring back is a major factor in spring operations. As an example, the tensile stress is maximum at the outside surface of the band and decreases toward the center of the sheet thickness. As we can see in figure 6.17, as you can see there, changing stress patterns in the band. The stress is zero at the neutral axis. The peak shape sketch in figure 6.17 depicts the change in tensile and compressive stresses in the bend zone. The metal nearest the neutral axis has been stressed to values below the elastic limit. This metal creates a narrow elastic band on both sides of neutral axis, as shown in figure 6.18. That a method to overcome or counteract the effect of spring back are overbending, bottoming, or setting stretch bending. Figure 6.18 is same as figure 8 and 6.17 in the first figure. Then we got figure 6.19. 6.19, essential components and mechanics of a figure is a compression bending and B is the draw bending. Bending may be done manually or with the aid of machine power, depending on the section thickness, the ductility of the stock and method employed. For example, compression bending and draw bending of tube is commonly done manually. In compression bending, one end of the workpiece is fixed in place relative to a stationary bending form, while a movable shoe or roll compresses the section against the form. Is draw bending, the workpiece is clamped to a fixed form and wiper shoe revolve around the form to bend a workpiece. As you can see in figure 6.19a, the bending of bar and tube. The four basic methods of bending bar and tube stock are A. Compression bending, B. Draw bending, C. Stretch bending, and D. Roll bending. In figure 6.20, we can see a principle of stretch bending. One benefit of stretch forming is that it elongates the metal throughout the section. As you can see, there is a cam, a stationary form D, and the clamp. Horizontal plane, the top roll bending roll is lowered toward the plane of the bottom rolls that make the bend. Roll benders may be powered, driven machines, or manually operated. As you can see in figure 6.21 is the roll bending picture. Yep. Then we get to figure 6.22 is the mechanics of the deep drawing of a cylindrical cup. Then we got figure 6.23 is the forming limit diagrams. A picture is a change in shape of circle on the surface on a sheet when drawing, stretching, or plane strain deformation occur, and B is a forming limit curve for different sheet metals. Next we get 6.6 powder metallurgy. Powder metallurgy, or PM, is a growing branch of metallurgy based on the production of material in the form of metal powders and the manufacturing of parts from this material. The primary market for metal powder is for parts manufactured by various PM technologies. However, metal powders are also produced by other applications. For example, approximately 10% of iron powders are used for producing welding electrodes. And various powders are also used in diverse applications. For example, copper powders are used as pigment for marine paints and as additive for metallic flake paints. Aluminum powder is used extensively for explosive and pyrotechnics. There are also other methods of powder compaction, such as metal injection molding and high temperature compaction technique, such as a hot isostatic pressing and powder forging. They consolidate metal powder to higher densities approaching or equaling that of wrought product. A general comparison of this PM method is summarized in table 6.5 that I also make there. And sintering time and temperature are the most significant factor from a practical perspective, with temperature being the most important variable. Particle size, compact porosity, and the powder type also influence sintering practice in table 6.6. Powders. Iron powders constitute the largest share, where over 80% of iron powder are used for PM parts. Copper and copper-based powder follow iron in volume of powder used in PM fabrication. Approximately 45% of all copper powder is used in the manufacture of self-lubricating bearings. This also is used as elemental addition in various PM parts. Another 40% is used for making hardware that require both decorative finish as well as corrosion resistance. Fabrication of parts by PM method has several advantages that include: A is a producing part with more uniform microstructure and distribution of alloying elements. B, high volume production of part with net shape or near net shape dimension, thus reducing the need for machining. C is a flexibility in component design. The design flexibility with PM is quite remarkable in the production of parts with many grooves, tapers, curves, and multiple level gear assemblies. Next we got 6.7, the material removal processes. Material removal processes, of which machining is a special class, are secondary manufacturing operations used to achieve precise tolerance and controlled surface finishes. Machining is used to convert casting forgings or pre-formed blocks of metal into desired shapes, with size and finish specific to fulfill design requirement. Machining operation can be costly compared to most other manufacturing processes because they are relatively slow to perform and often require substantial investment in overhead and skilled labor. However, the necessity of machining is the driving force behind continual improvements in productivity with better cutting machines, enhanced design, better tool materials, and an understanding of how the workpiece impact machining cost and quality. Surface integrity involves the study and control of both surface roughness or topography and surface metallurgy. The condition of the surface and the subsurface regions' structural components can have a significant influence on their capability to withstand the applied stresses in high stress or critical application. For example, fatigue failures almost always nucleate at or near the surface of component. Stress corrosion is also a surface phenomena aggravated by residual stresses that may be produced during manufacturing. Examples of typical surface integrity problems created in metal removal operation include A. Grinding burns on high-strength steel aircraft landing gear components, B. Untempered martensite in drilled holes in steel components, C. Grinding cracks in the root section of cast nickel-based gas turbine buckets, D. Lowering of fatigue strengths of part processed by electrical discharge machining, E. Distortion of thin components, and F is residual stress induced in machining and its effect on distortion, fatigue, and stress corrosion. Next, we get to 6.8 joining processes. Joining involves the use of mechanical, chemical, or physical force that keep two parts together. Mechanical methods are based on various types of mechanical fasteners, while adhesive bonding use chemical bonding, perhaps with some physical or mechanical factors. Physical methods of joining include welding, brazing, and soldering. The focus here by necessity is only a brief overview on the wide-ranging technologies of welding, brazing, and soldering. A general comparison of the basic joining technology is summarized in table 6.7, which is not very necessary. The main distinction between welding, brazing, and soldering is the nature of the bond in welds. Joining occurs by interdiffusion of atoms from like base material and forms bond. Then we get 6.8.1 welding. Welding is an ancient technology dating back to as early 2000s, with the practice of forging welding where metals are heated and pounded to cause permanent deformation, and bonding, forging welding is still performed, but many other more advanced welding techniques are currently available. The two basic categories of modern-day welding methods are A. Fusion welding and B. Solid-state welding. As we can see in figure 6.26 is a sealed metal arc or stuck welding. Then we got figure 6.27 is an example of components produced by gas tungsten arc welding or GTAW. A point is thin walled aluminum and B is titanium components. Gas tungsten arc welding, or we can call it GTAW, in this process also known as tungsten inert gas or TIG. Welding heat is produced between a non-consumable electrode and the workpiece metals. Because the electrode is non-consumable, weld can be made by fission without an addition of filler metals. Although filler metal is often used in these processes, the electrode weld pool, arc, and heat affected zone are protected from atmospheric contamination by a gaseous shield provided by a stream of gas that usually inert or by a mixture of gases. The GTAW process is well suited for welding thin section, as we can see in figure 6.27, and foil of all weldable metals because it can be controlled at the very low amperage. Then we get to figure 6.28. It's a gas tungsten are welding courtesy of Lin welding. Submerged arc welding, or SAW, is a process where the welding arc is concealed beneath and shielded by a blanket of visible flux. As we can see in figure 6.29, is a submerged arc welding. In the A figure, we can see a process schematic. In B, it's a submerged arc welding of flame-cooked steam joining in the head to the cell of the inside a tower. 4 passes were made with the current 400 amperes at the speed of 356 millimeter per minute. And then we get to a figure 6.30, submerged arc welding of a wear-resistant overlay of quartz in electric. Figure 6.31 is schematic of resistant spot welding process, and figure 6.32 is resistant seam welding. Solid state welding. Not all welding is done by fusion, with melting, intermixing, and solidification fusion of the metal being joined. Atomic bonds can also be formed by solid state welding, such that frayed surfaces coalesced and bond at temperature can be low and melting point. The bonding process is based either on deformation or on diffusion and limited deformation, so that atomic movement creates new bonds between atoms of two surfaces. For the next picture, we got figure 6.33 is typical example of A equipment and B schematic for resistant projection welding. Tooling is plane mounted and consists of water cooled copper blocks, welding die insert, and locators. Yep. And diffusion welding depends on the thermal motion on diffusion on atoms between surface. As we can see in figure 6.34 is relative regimen of time, temperature, and delumization for solid state welding process. And next we get figure 6.35 is the friction stir welding processes, a process schematic. And B is weld zone showing regions of heat effect zone, or HAZ, and thermomechanical affected zone, or TMAZ. Next we get 6.8.2 brazing and soldering. Brazing involves joining solid metals in close proximity by introducing a liquid metal that melts above 150 Celsius. A sound brazed joint generally results when an appropriate filler alloy is selected. The parent metal surfaces are clean and remain clean during heating to the flow temperature of the brazed alloy, and a suitable joint design that alloy capillary action is used. And then soldering. Like brazing, the substance material remains solid during soldering, and the melted solder distributes itself between the properly heated surfaces on the joint by capillary action. The solder reacts with the base metal surface and wets the metal by intermetallic compound formation. Upon solidification, the joint is held together by the same attraction between adjacent atoms that hold a piece of solid metal together. When the joint is completely solidified, the fusion between the base metal and solder joint continues until the completed part is cooled to room temperature. Mechanical properties of solder joints therefore are generally related to, but not equivalent to, the mechanical properties of the soldering alloy. I think that's all I got. Thank you so much.